Okay, so people, it was group 1, group 2, and group 4, right? Okay, so before we do anything, we're gonna actually make sure that everyone in your group has access to your code. So if you guys wanna go to your 2019 FRC, yada yada, Visual Studio Code. Yeah. Let me know once you guys have to go. Don't push yours just yet. Okay, so go to Git, and you should see a screen like this with changes. If you don't, please let me know. Okay, so then click. So this is important because this will make sure that like we don't overwrite each other's code. So go next to the Java files only. So they'll have the .java next to them, and press the plus. And it'll be something called staged. So now one person from each group, the person who wrote the code last time, type in like first like week 2 code. And press the check mark. Save all. And wait for it to commit. So once it commits, like I just changed it. So once it commits, you should see this little up arrow down here. So once you've committed it, click that little thing. Let's see, do I have to zoom in? That little thing next to the branch. Whenever, for any future lessons, all the code that I write will be in this branch called demo. So if you press the little branch button, it should say like group 1, group 2 right now. And you see origin/demo. If you click on that, all of the code that I've written will be loaded in. But please don't write any code in origin/demo because that's just for me to give you my code. So write your code in your respective groups. So if you ever want to access the code at home and you can't see it on the video, that's where you can access it. So everyone who has the capability of push their code, so we're going to get started. Okay, so quick review, because it's been a while since the last workshop. What motor controllers do we use?
The Talons.
Yep, we use Talons. How do most electrical components on the robot CAN? Yep, CAN. And what does CAN stand for?
Controlled area network.
Yep. How is CAN typically wired? Not how we wire it, how's it typically wired?
Like 2 wires, 1 wire, I don't know.
Yeah, so basically you take the green wire, or one pair of wires from one motor connected to the other one, and then wired in it's called a bus configuration. How's our CAN wiring different?
We use a parallel circuit, and so like if one thing breaks, the others don't.
Yeah, so essentially we put it all into one hub,
Oh.
so if one thing breaks, then yeah. And what tool can you use to get CAN IDs? So it's actually a tool that WPL came out with. It's Phoenix came out with, called the Phoenix Tuner. And I think I'm going to show you guys how it works, because I wasn't able to do it last time.
Where's the hub?
So the hub, wait, actually, it's probably good. So everyone come over here. Let's point out the Talons. So we talked about Talons. Our Talons are down the side over here. So as you can see, one side of the Talon, usually with green and white wires, are connected directly to the motors. And that's how the motors get power. And the other side is connected to this thing. It's very hard to see because the electronics are very messy, but it's called the PDP. And the PDP essentially distributes power throughout the robot. So the Talons, when you're wiring them up, you have one side going to the PDP, and then you have the other side going to the motor. And these green and yellow wires here, that's the CAN. So normally, let's take a Talon, let's take this one because it's kind of easy to see. You have this pair of wire, and then you have this pair of wire, right? You have 2 pairs of wires.
They're both cans.
They're both CAN. So there's 2 pairs of CAN wires going out from one Talon. Normally what you do is you take this wire and connect it to the other pair from this side. But what we did instead is we terminated one side, then we just wrap it in electric tape, doesn't go anywhere. And we took the other one and connected it to this hub over here. If you guys know. So this is our CAN PCB hub right here. See? And essentially all of the motor controllers are plugged into here, and then one set of wires is going from here to here. What is this? I'll put it
Power?
This is the
I2C?
This is the RoboRio. So this is what controls everything. So the information goes from here to this PCB over here, and then that distributes it to the motor controllers and the other components. So let's see if I can get two. And the other important thing, so this is the PDP. These are the talons. Let's see what else is important. So how many of you have heard of pneumatics? Okay, so pneumatics are essentially, they use compressed air to move a piston in and out, or move pistons in and out. So the way to control pneumatics is there's this little module here. It's called the pneumatics control module. So what that does is it'll take, so the pneumatics, the pistons are simple. They're either fully extended or fully closed. And if you want to come around here, there are these things called solenoids. And what solenoids do, or if they're on, then the piston will be fully extended. If they're off, the piston will be fully closed. So this is a double solenoid, which means it controls two pistons at once. So that's super useful for the claw here, right? Because when you're extending outwards, you don't want one piston to extend before the other. That's why we use something called a double solenoid, where they both extend at the same time, because both of them are either extended or both of them are either fully closed. So the pneumatics control module, what it does is it's connected to the RoboRio via what connects all the electrons. CAN. And when we call it, it'll tell the solenoid to turn on or turn off, and that moves the pistons. So probably the most important pieces electronically on the robot are the PDP in the middle, which
Distribute power.
distributes power, the CAN PCB, which
Is like distributes just instructions. For
so it controls CAN
everything.
basically. The talons, which
Control the motors.
solenoids, which do
Control the pistons.
pistons. And so one last thing, so we're going to talk about this later. So there are a lot of sensors on a robot. So this one right here, this is the linear actuator, it's called the DART. And it's controlled with something called a potentiometer. What a potentiometer does is it provides you it's a absolute encoder, which means that it provides you a listed value based on a static point. So normally when you think of an encoder, you think of, I'm going to measure how far I'm going to go. So that's something called a relative encoder. What that does is it zeroes out on where you start, and it counts the ticks after you start moving. But an absolute encoder like this, it doesn't zero out when you power on the robot. It remembers where it's been. So that's super useful in setting start position and setting stop position. So you don't have to reset that every single time. Because let's say you accidentally power up the robot and it's like the claw's out here, it'll still remember to go back to its initial position. You don't have to reset all that. So that's one of the sensors, and that's the linear actuator. And so that's pretty much all the important electronic stuff on the robot. Look around. Yeah, the wiring wasn't great this year, but so there are probably 4 or 5 main. Oh wait, did I talk about the VR? No. So we have the PDP, right? So that distributes power to all the devices. But there's a difference between power and voltage. Power just makes sure they have power, but then if you want to limit like currents and that kind of stuff, that's where the VRM comes in. It's the voltage regulator module, I think that's what it's called. And it basically regulates the voltage of all the electronics on board to make sure nothing fries, that kind of stuff.
So this is another question. Are you gonna restart from scratch on the next robot this year?
So most of the electronics, like the PCBs we reuse, there's no need to make new ones. But depending on what mechanical team actually builds, electronics will be vastly different.
Okay,
So in a way we restart, but in a way we reuse the same things.
Okay.
And you'll get familiar with this robot, because most of the season, and probably till the last half of build season, we're going to be programming and testing on this robot. And then once they actually build something for us to use, that's when we actually
So you use this as a test robot rather than a one for competition?
No, this was our competition robot last year, but next year it'll be used as our test robot. So basically the previous year's robot will be used as test and demo.
Okay.
So this is what Phoenix Tuner looks like. It's just a little widget. So once you open it up, make sure you're connected to the Team 5338 Wi-Fi, and you can click force start the server if it didn't start. Actually, yeah, no, click force start, and once it says okay, the server started. So then you should be able to click CAN devices and it'll open up a page like this. You can see that each ID, which is the PCM, what does that do?
Distributes power.
No, that's the pneumatics. So that tells the solenoid whether they turn on or off. So that has its own ID. The PDP, which does distributes power. And then you have all of your talons and motor controllers. So in code, you remember it says WPI talon SRX and parentheses ID. So you'd see talon, this is your ID. You'd find your talon, you'd find your ID, and you put it there. So if you guys want to go back to the robot, and let's say I want to find talon 2, right? I can actually blink that talon, and you'll see one blinking differently.
Oh, the talon's in the back?
Yeah,
Okay.
so then that talon is ID 2. So then if you're like, okay, I want to control my drivetrain, you try to blink the talons that are associated with those motors, and that's how you figure out this is how I control the drivetrain.
I can't find number 2.
So here, let me try to blink one that's a little bit easier to see. Is that easier to see?
It'll blink pretty fast,
yeah,
right?
I see. So it blinks really fast.
It'll blink really fast over the course of this thing. So that's just the neat tool. Normally we'll pre-label the talons beforehand, that way you don't have to go through this device every single time. But let's say there's CAN issues during competition or something like that. This is one of your best friends because it'll help you figure out what's wrong, what devices isn't the robot seeing. Because this is essentially from a RoboRio point of view. So it's like, this is what the RoboRio sees. If it's not on here, the RoboRio doesn't see it, something's wrong. So this tuner can also do a lot of other things. So it can also do self-test. So if you can actually pick a motor or pick a group of motor and click self-test. And once the motor runs, it'll actually create a graph of the position and velocity of the motor, allowing you to determine, let's say you're doing speed regulation or something like that. Is your code working? It's an easy way to do that. So that's Phoenix Turner. It'll be tuner. I don't know why I keep saying Turner. Tuner. It's a nice and easy way to make sure your CAN is working. So that was Phoenix Turner. So now let's go over. So I think we're pretty much done with the electrical stuff on the robot. So go back to your groups. Okay. So quick programming review. What class does all the driving code go in? This is important. Drivetrain, yes. So what object can I use if I want to make a motor move?
IO? OI?
No, what? Not what class, but what object? What is it called? It's the same thing that actually physically controls the object. Talon SRX. So how can I group motor controllers together? There's two ways that you can group motor control.
There's a class that allows you to be grouped.
So there's two of them. Okay,
There's one that
name the
controls
two?
all four and the one that controls
Yeah, so there's
each side.
speed controller groups, which allow you to group two motors together, and then there's something called differential drive, which allows you to group two speed controllers together. So we talked about this at the end, how can I link subsystems and commands? So at the end of your subsystem, this should already be there if you created it using WPLib. There's a little command called init default command. And in there, you say set default command and new your command. Remember, in our command, what we did was we said we required the drivetrain, and then we initialized it. So essentially what this does is the scheduler, which is, what is the scheduler? It's from 2 weeks ago, but let's see your words. What's the scheduler?
It switches the mode from command to autonomous.
Yep. So the scheduler only runs commands. So if we wanted to recognize our subsystem, we have to create a command that says, here, this is my subsystem, run. So essentially, that's what this init default command is it allows you to link a subsystem with a command. So you can say command start subsystem, something like that. So now we're gonna get into sensors. So driving by itself is great. Oh wait, current limiting first. Okay, so one thing that I forgot to talk about last time is when you saw the VRM and you saw the electrical components that can limit current. But when you have a lot of mechanical motors and you have a lot of talons on your robot, you have to limit current in code. And there's a pretty easy way to do that. And it prevents the motors from getting burned out. It prevents too much current from flowing through the PDP. And it prevents like the breakers from popping. So if you want to come back over here. So on the PDP, I don't know if you see these little black things over here.
Oh, I see them.
So those are physical components that help prevent too much current from flowing through the PDP. So if there's too much current flowing through there, the breaker will pop, and that'll just break the connection and prevent more electricity from flowing through. So it's really loud and you can hear pretty well. We had a lot of breakers pop this year. And essentially the PDP, a little more information about that. There's two separate circuits, if you will. There's one that supplies more power, so the drive motors, the elevator, which has to lift our robot, that's going to be on the high-powered circuit with a higher amperage breaker, which means that more current can go through, which means the more torque and more power you can get to your motor. And then there's the low amperage current, which are the ones back there, where you have the stuff that doesn't need that much electricity, like the line light up here, that doesn't need that much, so that stuff goes on the low amperage. When you have a lot of motors like we did this year, you have to put motors that might require high amounts of power on the low amperage circuit. So that's where current limiting comes in super well, because you had to make sure that it didn't draw too much power and pop the breaker. So the way to do current limiting in actual code is, it's not too complicated. I'm too lazy to type. So if you guys want to add this to your group 1, group 2, whatever groups you're in, that's right. So you can just create a command called configure talon. That's what we typically do. So essentially you can do talon, which is just the class in general, or a talon that you created, dot config peak current limit. So there's two types of current limiting they can do. One of them is peak current limit. That means that throughout the entire competition, the maximum current that can ever go through there is 100 amps. But then there's also something called continuous current limiting, which means that at any one point, you can only have a maximum of 80 amps. So this is a soft border. So essentially you have two borders. One where it's like, one at 80 amps where you're like, it shouldn't go above this. But then you have one at 100 amps where it's like, it definitely shouldn't go above this. So it's just a double border to prevent something bad from happening. And you can see config peak current duration is at like 3 seconds, which means that it only happens at like, it'll give it like 3 seconds before it pushes it back down to the continuous current. And this deadband and the frame period, essentially, that means that we don't want like minute electrical signals to cause something, so you just create a dead zone where you just have like, so that the tiny electrical signals won't actually cause movement in the motors. So I know that's a lot, so if you guys want to copy that down in your drive train.
What does current limit do?
So current limit, it essentially prevents too much electricity from going through.
Oh, okay, that's just
Yeah.
just that.
And if you can't get all of it down, it'll always be in the demo branch.
Is the demo branch updated with the code from last year?
It's not updated with the code from last year, but we're gonna work our way up there. So by the end of the workshops, it should have most of the stuff from last year. So then once you have the method written down, I'll come back to the method to get this done. You can actually create the constructor, which is essentially the initialization code. So public drive train. And you can say, you can actually configure all of your, you can configure talon, and then you can configure all your talons in specific order. So I'll go back. So although driving with motors might be good enough, when you're actually, a lot of FRC comes down to doing stuff autonomously without too much driver input. So sensors are a great way to do that. One of the most common sensors that we use are the gyro sensor. It's the NavX. So if you want to come over here, I'll show you the sensor. Sorry, a lot of walking today. So the NavX, or the gyro sensor, rests right on top of the RoboRio. And you can see it's covered in a blue case. But inside, it looks like the bottom picture over there. And essentially, it allows us to determine what direction we're facing, whether we're tilting back and forth or side to side. So there's three major axes that the gyro sensor records. X-axis, Y-axis, Z-axis, also called pitch, roll, and yaw. So pitch allows us
Take
to
it
measure
mobile.
whether the robot's tilting back and forth. Roll allows us to measure whether the robot's tilting side to side. And yaw, which is the one that we use mostly, allows us to measure how much a robot is turned. Because the z-axis, if I'm moving around the z-axis, right, because the z-axis goes up, if I'm moving around the z-axis, it allows us to see how much the robot is turned. If I'm moving along the y-axis, which goes out that way, back and forth, and if I move across the x-axis, which is that way, side to side. Or did I flip that? Yeah, side to side. So generally we use yaw, and this is the NavX sensor was the one that we use, which is the one that we use. It's created by HRS, and there's a library for that, so let's get you installed with the library. If you guys have your computers. So go to tinyurl.com/5338 links. So this is important link. So copy this NavX installer link. It's the
Where's the tiny URL? What's the tiny URL?
tinyurl.com/5338 links. So that'll take you to this Word document. So copy the link and then go to your drivetrain or your code base.
The second link?
Yeah, the second, the one that says NavX installer. And click on the little WPI lib logo. And click Manage Vendor Libraries. Okay, so once you've clicked on that, click Install New Libraries Online. Install New Libraries Online. And paste in the URL that you copied. And press Enter. So once you do that, click Terminal.
So he got a thing that says recommend that you run a build after the vendor.
Yeah, that's what I'm going to do. Yeah.
okay.
Okay. Was everyone able to copy the link? And press enter. Okay. So now click Terminal, New Terminal. So open up a terminal and type in /.
Well, what should they do with the message?
Just close it out.
Just say yes or no?
Yeah, just say. Oh wait, this is automatic.
Keep closing it, sorry.
Did you just close it? So terminal, new
Am I
terminal.
supposed to do yes or no to that message?
Just say yes. Yeah. I didn't. Yeah. Okay. So now go to your terminal. Yep. Click on it. Now type in /. I mean, you don't have. You just ignore the message. We're building it anyway. So do /. Gradle W build. Press enter, and it should download the library. So now, if you want to, so now what we typically do is when we program sensors, we have drivetrain, subsystem called drivetrain. We have a new subsystem called sensors. So if you want to right click on your subsystems, create new class or command, subsystem, and type in sensors. Got that and create that. Whoever created sensors, so the way we define our gyro sensor is an HRS. So public final HRS equals new HRS, and these are just information about the NavX that we have to pass in. Just not too important where we got that. The HRS is pretty simple to use. So since we created our sensor subsystem, we have to go into Robot and actually define it. So static sensor equals new So then once you import it, or once you define it in robot, you can go into drivetrain or any other class, and let's say we have our drive method, right? You can say robot.sensors.ahrs.getYaw. And what was yaw?
The z-axis.
Yeah, so it measures turn. So essentially what this will do is it'll tell you what heading am I at. So it's kind of fast, I'll just go through what I just did. So I defined AHRS in a subsystem called sensors. I said while this is calibrating, don't do anything. Then I went into robot.java and I defined my sensor object. Because FRC programming is object oriented, so you have to define your object. And then I went into drivetrain and I said, give me the yaw. So if the robot's running, this will output the direction that you're facing. And that's pretty much all the programming that is for the gyro. So you'd say something like, while robot.sensors.ahrs.getYaw, while it's less than 180, drive negative 0.5, 0.5. So while the heading is less than 180, turn. So that's a simple command on how you can use the gyro sensor. And this is super ineffective because it overshoots, right? So if you're just turning and the sensor says 180 and you're stopping the motors, what happens?
The momentum carries over.
It'll momentum carry over. So next time we're going to talk about algorithms that you can actually use to make turning a lot more accurate. Because if you just do this, although this will work to some degree, it'll skid because the momentum will cause it to overshoot. So there are algorithms that you can use to have it turn more accurately, but this is just a simple way that you can use the gyro sensor. Another important sensor that we use very often are encoders. So we use something called SRX9 encoders, and what they do is they measure how much a shaft has rotated. And they allow us to determine how far or how much distance we've traveled. And the good thing about these is they use the Talon library, which most of you already have, so you don't have to download anything else. And they're also using autonomous because it allows us to say, okay, if I want to get from here to there, how far do I have to go? How far have I been and how much farther do I have to go? And they use known parameters like distance and allow the robot to move like we want it to. So there's two types of encoder input. I talked about this earlier. There's relative encoders and absolute encoders. So relative encoders, they reset every single time you power them on, which means that it tells you, I'm here, this is how much distance I've traveled after I powered off. So when we get to actual programming, you use something called .get quadrature position. And quadrature position is just a type of relative encoder, where it tells you this is how many ticks I've gone since I powered on. And the cool thing about quadrature encoders is that when you're programming and coding, there's a lot of dimensional analysis and like conversions involved. So there's 4,096 ticks per rotation of the shaft. So, quick math question. If I want to go 6 feet, how would I find out how many ticks that is? And if the diameter of my wheel is, let's say, 6 inches. So if I want to go 6 feet and I want to get it into rotations, what do I divide by? The circumference of the wheel. So if my diameter is 6 inches, what is my circumference? 12 pi. Or yeah, 6 pi. So 6 pi. So I divide whatever distance I have by 6 pi. That's one rotation. If there's 4,096 ticks per rotation, what do I multiply by? 4,096. So I take my distance, divide it by the diameter times pi, and I multiply by 4,096. That'll tell me how many ticks of my quadrature encoder I need before I can get to where I want to get to. But same thing with the turning. What happens if I just use the encoders? I say stop the motor when I get to this many ticks.
Overshoot.
It'll overshoot. So same algorithm, which we'll talk about Saturday, it'll tell you how much before the target do I have to slow down so that I stop at the target. So that's the other encoder. The other encoders are called absolute encoders, where when they're created, that's when they start, and they remember their position even after you power them off. So an example of that is the potentiometer that we have on the dart. It'll remember its position when it powers off, so you don't have to reset it every time. Typically, when we're driving and stuff, we use quadrature encoders, but like for stuff like the dart, we do use absolute encoders. So let's actually get to programming this. So if you actually go, so this is, it's pretty simple, the code for encoders, is if you go to drivetrain, and you go to, let's say, drive again, you can say, so each encoder is plugged into a Talon. So if you want to come over here, we can actually, it's hard to see the encoders because they're hidden behind the gearboxes, or actually no, these ones are. So these are the encoders right here, if you want to come take a look. So these are attached to the shaft, so every time I rotate, it'll count the ticks. And each encoder is pre-wired to one of these Talons. So this one, I believe, is wired to this Talon right here. This Talon right here. So in order to get the input, you reference this Talon and get the analog input from that. So if you want to go back to here, so you can say, let's say left one, right? That's the Talon. Let's say that's the Talon that we attach it to. Dot get sensor collection. Dot get quadrature position. And where does that get you?
It gets the position after it boots up.
Yep. So that gets you how much ticks have gone. So let's say that's important to see how far you've been. But let's say I want to go multiple distances. Let's say I want to first move 6 feet, and then I want to move 3 feet after that. One thing you can do is you can say left one dot get sensor collection dot reset set quadrature position, right? And you can set that to 0. And what that essentially does is that says reset my encoder. I've gone 0 ticks from my current position. So if you want to change the distance, you can say, okay, while this value is less than, let's say we want to go 1 rotation, right? 4,096. While it's less than that, drive at 50% power. So again, this does not account for momentum. So this will be inaccurate. Let's say we want to go for about a rotation. So while left one, which is we're supposing is the motor that the encoder is attached to, the get sensor collection, the get quadrature position is less than 4,096, drive. So now let's say we want to go 2 rotations after that. We reset the quadrature position, so that means it thinks, oh, I've gone nowhere. And then we can replay this method, except instead of saying 4,096, let's say I want to go 2 rotations, so that's 8,192. Hopefully, my math checks out. But yeah, what this does is it'll tell the encoder, okay, I want to reset my ticks. I've gone 0 ticks, so then I can go a different distance. And that's especially useful when you're going straight, turning, and then going straight again, because you can say, I want to go forward 1 rotation, use the AHRS to turn 90 degrees, reset my encoders, and then go forward another 5 feet. Because the thing is, when you're turning, what happens? Even when you're turning, what is happening to the wheels?
It's one is going one direction and the other is going the opposite.
Exactly, but it's still, the encoder is still counting those ticks. So after you're turning, you want to reset the encoders, which allows you to get rid of that error that you might have from the wheels turning, the encoder moving while turning.
Is there something that you can do with the encoder so that like it doesn't count any ticks while you're turning?
You could set it. You could like disable the encoder while you're turning, but it's a lot easier to just reset the value. So there's a way to disable the encoder when you're doing certain actions, like saying while I'm disable this encoder, that way it doesn't count it. But it's definitely a lot easier to use it. So that's just the general way. So encoders will be your best friend, but doing this way, just saying well less than encoded, that's very inaccurate because, like we mentioned before, momentum. So that's where we're going to get into algorithms on Sunday, talking about how can I control that? How can I make sure I won't get the robot where I want it to get? So now that we talked about encoders and gyro, the RoboRio, this part is cut off. So the RoboRio, the encoders and the gyro sensor, so the gyro sensor goes here, right? It just lays on top and it connects to these pins, and that's the AHRS. The encoders are connected directly to what are they connected to? The motor. So they're connected to talent. So the RoboRio does not take that input. But what the RoboRio does take in is it can take in digital input and it can take in analog input. So there's two ways of getting analog input. One of them is to connect it directly to the RoboRio, and the other way is to actually connect it to something called a Talon breakout board. And what that does is it allows us to connect analog input directly to the Talons. So that way, if you want to go back to the code, so this is what we do with the potentiometer, because essentially, when you're connecting a sensor to a motor controller, it makes it a lot easier, because it's like when this motor reaches a certain point, stop this controller. So you're not dealing with different streams of input, it's just all from one place. So if we connect something, let's say the dart to the...
What's the dart again?
So the dart is this linear actuator that controls the clock.
Oh, okay.
So let's say we connected the potentiometer and the dart to a motor. We could say, let's say we connected to left 2 this time, right? So left 2 dot get sensor collection dot get analog input. And that essentially gives you the absolute encoder that's attached to the breakout board. And essentially, you can do the same thing while it's less than a certain value, move the motor.
The encoders are attached to the talent itself, right?
Yes.
And the talents are attached to the PI, the printed.
The RoboRio through. So you can say while this is less than a value, you're gonna have to tune this value. Obviously, left 2 dot set 0.5. So while it's less than the value, move the dart. But then again, you run into the same problem with momentum, so you have to use other algorithms to figure it out. And the thing is, so you can do all of this in drivetrain, right? But when you're using autonomous, you're going to be creating more subsystems and more commands. So a lot of the sensor stuff, like reset encoders, right? That'll be done in sensor. So you can create a command where it resets the encoder for all the talents that you're currently using. So that's just the way that we organize it, but because doing it all in drivetrain, that makes it very messy. And the last sensor that we're going to use. So just real quick, what sensors have I gone over so far? Gyro, which is using.
Rotation.
And what library does it use? AHRS. So AHRS dot get what?
Yeah.
Get So the second one is
Encoders.
and that uses
Get sensor.
sensor collection dot get what?
Get quarantine position or get quarantine.
Quadrature
velocity.
position. It's quadrature position, quadrature velocity. So the third thing are the potentiometer, which uses get sensor collection dot get what? Analog in, because it's analog input. So the last thing is digital input, which are stuff like switches. Switches are a great example of digital input because it can either be on or off. There's no range of values for that. So essentially, if you guys want to come over here, I'll show you how the switches are wired up. So the switches, essentially, they have 3 pins, and they're wired to the digital input slots directly on the RoboRio. So in order to program that, you could just say, get me the digital input from the RoboRio slot 1, because each of them are labeled, and then that gives you a Boolean value of whether the switch is on or off. and that's how you program that.
So wait, is the what's the thing that controls all the columns again? So is the CAN connected to only one port? And then
So no, the CAN, so all the,
I'm talking about on the Rio.
so on the Rio, yes, there's one CAN port on the Rio because it's a network, right? So
Yeah.
you have
Yeah,
one
yeah.
device connected to that network. But the thing with digital input is it's not connected via CAN, because it's not using any of the towns.
Alright.
So it's plugged directly into the floor. So in order to actually program that, I believe you can say, so if you go up to where we defined our variables, you can say use digital input switch for new digital input. And you can say something like whatever ID you have. Equals, and then you can just leave it on one, and then you can say limit dot get, and that gets you a Boolean value of whether the switch is on or the switch is off. So this is on or off, depending on how you're using it. So let's say you're using it as a limit switch, you could say while limits dot get, do whatever, do task. But once that turns to false, which means once you hit it, then don't do the task.
So when it gets no limits, does it return
So
false?
what the get does is if it's not hit, that returns a true, because it means if the limit switch isn't hit, do whatever you want it to do. But once it hits, the value becomes false and forces you to get out of that loop. So that's a pretty simple way to program limit switches. So let's see what else. So those are the major sensors that we use, and so yeah, potentiometers, like I said, they're absolute encoders, analog input, yada yada yada. That digital input, the Boolean of whether it's on or off, and there's two ways you can use digital input. One of them are limit switches, which means that if I'm touching the switch, the mechanism shouldn't be able to go on any further. So that was especially useful with our elevator, because if it went too up, it's gonna run into this metal plate over here, and it's gonna break the mechanism. So we said if it's hitting the limit switch, I shouldn't be able to go up anymore, and if it's hitting the limit switch down, it shouldn't be able to go down anymore. So that's a good example of switches. Another example of switches are the little yellow things that you see on the side of a robot. They're called optical switches, which means that if something is in front of it, then it's on. If something is not in front of it, then it's off. And can someone tell me an advantage of using switches as opposed to something like encoder? There's one major advantage.
No, I don't know.
So basically, the major advantage of using a switch is that you know where the position of the mechanism is. If it's hitting the switch, you know exactly where it is. So there's not as much tuning involved. Because for an encoder, there's stuff like momentum, which could carry you forward. Because it's the encoder values and analog and potentiometer, that kind of stuff, it returns a range of values. Not something that's on or off. So for a switch, if it's off, you know that's exactly where it is. So let's say you're moving an arm, although we used it last year, you can say it as you will, but if the optical encoder is on, the arm is at a given position, there's very little tuning involved. It's going to be pretty much where you're at it. Well, if you use something like encoders, there's a lot of other factors that could take into play.
So you could also use a switch as potentially a signal to zero your encoder, right? So
Yep.
if you know your position, you hit the switch, you
Zero.
say zero your encoder,
Zero
and you know where you
encoder,
are.
And then you
Yeah.
do minute changes from there. Okay, so I think that's all we're doing today. So like I talked about, what to look for next time, and a lot of these sensors, they don't take into control the movement of the object, like the velocity, momentum, that kind of stuff. So there are algorithms that we've created, or that people have created, that allow you to be more precise. Because the main thing about robotics and like programming and autonomous is you want to get your robot from point A to point B and move like you want it to move. You don't want any external factors to cause it to move differently, because when you're programming, you have to be very precise, and the robot will only be able to do the task if it gets to a certain position. So there's certain algorithms that are created to figure out how to get to that certain position. So I think we're done for today.